CERDIP's Statement of Need has a stated goal of fostering the development of innovative, destructive approaches to treat investigative derived waste, or IDW, from investigations of per- and polyfluoroalkyl substances, or PFAS, contamination in the subsurface. IDW includes excess soil cuttings, purge water from groundwater sampling, and fluids from decontamination of drilling equipment. The purpose of this project was to demonstrate that smoldering combustion can achieve temperatures needed to treat PFAS in soils and IDW. Smoldering combustion is a flameless, self-sustaining process that occurs on the surface of a condensed, that is a solid or liquid phase, fuel, converting organic materials into primarily heat, carbon dioxide, and water. Smoldering has been well documented for solid porous materials, and burning charcoal in a barbecue is a familiar example. Smoldering of an organic liquid, such as a non-aqueous phase liquid or NAPL, that is embedded within an inert porous matrix is also possible. After a one-time local ignition, the smoldering reaction continues in a self-sustaining manner that destroys the contaminant if an oxidant, such as oxygen in air, is continuously provided and the contaminant acting as a fuel is in sufficient quantity. The self-sustaining nature makes smoldering very energy efficient and therefore cost-effective, as energy is only added at the start, unlike incineration approaches that require continual energy input. The temperature obtained through smoldering can be significant and exceed temperatures needed to destroy PFAS. However, unlike solid or liquid fuels, PFAS are not contaminants that can support smoldering combustion in of themselves. Therefore, the objective of this study was to evaluate the use of a surrogate fuel that can support the smoldering process that achieves temperatures greater than 900 degrees Celsius, which is sufficient to destroy PFAS compounds. This study was conducted in two phases. In phase 1, 2 solid organic compounds, crumb rubber and granular activated carbon, or GAC, were evaluated as surrogate fuels to assess if they could smolder at temperatures greater than 900 degrees Celsius when mixed with sand. In phase 2, PFAS destruction was assessed when PFAS was absorbed to GAC and then mixed with sand, and when PFAS was absorbed to soil and was mixed with an uncontaminated or virgin GAC. For phase 1, a total of 8 column tests were conducted using specialty designed columns as shown in Figure 3 and 4 of the report. Smoldering was assessed through ignition, the consumption of oxygen and production of combustion gases such as CO2 and carbon monoxide, measuring the average peak temperature and smoldering front velocity, and whether self-sustaining smoldering was observed through either steady or increasing peak temperatures after the heater was turned off. Figure 12 shows the thermocouple profiles exceeding 1,200 degrees Celsius within a column when 60 grams of GAC per kilogram of sand was added, and the air flux velocity was 5 centimeters per second. Table 6 summarizes the average of peak temperatures and front velocity as the solid fuel to sand ratio, and the air flux was varied. GAC was found to be the best fuel surrogate and produced temperatures greater than 900 degrees Celsius when mixed with sand between 40 and 60 grams per kilogram of soil. Crumb rubber also worked but produced undesirable residues. As shown in Figure 15, the peak temperature is controlled by the GAC concentration, and Figure 16 shows the smoldering front velocity is controlled by the air flux. For Phase 2, 4 tests were conducted. The first 2 tests used 3 PFAS compounds, PFOA, PFOS, and PFHXS, that were absorbed to GAC, then mixed with sand to a target ratio of 40 grams of GAC per kilogram of sand. As shown in Table 9, prior to smoldering, the concentration in the GAC sand mixture for these 3 compounds was 590, 140, and 240 milligrams per kilogram in the first test, and 510, 120, and 220 milligrams per kilogram in the second test. The average peak temperature exceeded 900 degrees Celsius in both tests, and all compounds were non-detect at a detection limit of 0.4 micrograms per kilogram after smoldering. The second 2 tests examined the treatment of PFAS absorbed in a surrogate soil mixture with a known organic fraction. In addition, the column was modified to quantify the emissions of hydrogen fluoride and PFAS, as shown in Figure 11. One of these tests examined the treatment of the same 3 previously tested PFAS compounds, and the final test used 6 PFAS compounds, adding PFNA, PFBS, and PFHPA to the mix. For both of these tests, a virgin GAC was used as the fuel source, which was mixed into the soil mixture. In the first of these 2 tests, the PFAS concentration was measured in soil samples before and after smoldering, and hydrogen fluoride, or HF, and PFAS were measured in the emissions captured from the column. Table 11 shows that the analysis indicated that all PFAS was removed from the soil at a detection limit of 0.5 micrograms per kilogram. Furthermore, 82% of the available fluorine was captured as hydrogen fluoride, indicating decomposition of the PFAS. However, PFAS captured in the XAD tubes, or XAD tubes, was not to be quantified due to extraction limitations. In the second test, the PFAS concentration was measured in soil samples before and after smoldering, and Table 13 shows that all compounds were non-detect at a detection limit of 0.05 micrograms per kilogram. Unfortunately, a line leak prevented accurate capture of HF, or hydrogen fluoride, in this test. Small amounts of PFAS compounds were extracted from the GAC from the XAD tubes. However, the total amount of PFAS emitted cannot be calculated, as we estimated the efficiency of PFAS extraction from the GAC was approximately 50%. However, given the absorption capacity of PFAS onto GAC and the measured concentrations, it appears that the amount of PFAS emitted during smoldering is very small. The observed PFAS compounds in the emission suggest that there may be some conversion of the sulfonates to their carboxylate versions of PFAS, for example, PFAS going to PFOA. Although PFAS will completely break down at high temperatures with sufficient residency time, it is possible that during the heating there is sufficient energy to break off the sulfonate head group and volatilize a small fraction of PFAS. From a practical consideration, the emitted PFAS could be captured in an off-gas GAC treatment system, and the GAC subsequently used and treated by smoldering. The results of this testing indicate that PFAS can be destroyed via smoldering. Additional work was recommended to further improve the mass balance of PFAS destruction, as well as address impacts of soil heterogeneity on the smoldering process. The results from the study, combined with commercially available smoldering remediation technologies, suggest 2 real-world applications. 1, an ex-situ treatment of PFAS contaminated IDW or excavated soils or spent GAC containing PFAS, and 2, in-situ application to treat PFAS source areas or GAC used to create permeable sorbent walls to treat groundwater plumes of PFAS. As shown in the abstract figure A1, ex-situ treatment would involve placing a soil GAC mixture on a commercially available engineered system called a hot pad. The hot pad is a low-profile platform that supplies the heat and air used to initiate and sustain the smoldering combustion reaction. Soil mixing could simply be done using backhoes or other commercially available methods. The high temperatures that are achieved during smoldering also allows the destruction of other co-contaminants and allows treatment of wet soils. Off-gases would be collected and treated by appropriate off-the-shelf methods. As shown in the figure A-2, in-situ treatment would require the mixing of the GAC into the soil using traditional soil mixing technologies. This GAC could be mixed into the source zone that is located above or below the water table, or could also be mixed into soils to form sorbent permeable walls to intersect the PFAS plume in groundwater. Ignition points would be installed post-soil mixing along with vacuum extraction points and off-gas treatment system. A downhole portable heater inserted into the injection point is used to initiate the smoldering process and supply air, which is maintained by the addition of air through the injection point. Application of in-situ smoldering is also commercially available.